Okay, so based on my record, this should be the one in 2021. So May or June 2021. I don't know which version it is, either the main or maybe the listed one. As usual, the first question, main part is about transformer. And there are two sections here, two more sections, which are descriptive questions. Sometimes you see, instead of those descriptive questions, there's a question about fault management. There's, for example, a network, some normally open switches. So here, again, section A and section C, you can find discussions in the lecture notes, but I think we also discussed it in the previous weeks. Very brief, why do we use per unit system? You can say simplicity of the calculations. Also, when you go for transformers, the impedance of transformers are the same on the two sides if you go for per unit system. And resistances, why are they ignored? We have several reasons, like static loads would be removed, or resistances of cables or transformers are removed, mainly because they are much smaller than the reactances when it gets to the fault calculation. But you have more discussions in the lecture notes, so you can look at that one with details. This is actually the part which needs numerical calculation, and usually we give a transformer with its impedance or reactance. The leakage reactance is actually the total reactance of the transformer, power, and the voltages, the rated voltages. The first question here is, what's the actual reactance? When they say actual, it means ohm, okay? Sometimes we may say ohmic reactance, sometimes we may say actual. It's the same as fault or power. Sometimes you say actual power or actual fault. That is in ampere or MVA. So, actual reactance in ohm with reference to the low voltage. When they say low voltage, that means you need to go to calculate the low voltage base impedance. Low voltage base impedance. First, you need to calculate it. So, XLV is the question. We need to know what is XB, the base impedance or base reactance. Always reactances equal V squared divided by S. So VB squared divided by S. We just need to be careful which side of transformer we are calculating. Here they say low voltage, so obviously you need to put 20 kilovolt. So 20 kilo, 20,000 square divided by 450 million volt amp, because that is the power, the rated power of this transformer. So you get 0.88 ohm as the reactance, as a base reactance or base impedance. Now, based on definition, actual quantity equals per unit quantity multiplied by base quantity. So per unit multiplied by base. Per unit is 20%. So we put 0.2, and then the base is 0.88. So you multiply and you get 0.18 ohm. This is ohmic or actual reactance. We need to do the same in the second section, but for the high tension side. So it's high voltage. So 230 kilovolt. Now, again, we need to calculate X base or base impedance or base reactance, VB square over S, 230,000 square divided by 450 million volt ampere. You see, when we go for this formula, as here we make the square of voltage. If the voltage is in kilo, like kilovolt, you make the square, kilo will be like 1 million, because 1,000 square is 1 million. And if you have S in mega, like megawatt or megavolt ampere, That is also million. So, for simplicity, if you like, if voltage is in kilo and S is in mega, you don't have to do this kind of calculations because anyway they are crossed out. So you can simply put 230 square divided by 450. But be careful, this is only when you go for base impedance or base reactance. Why? For calculating base current, there is still 1,000 remained by that S, because I, or I base, equals S over root 3V. So if I base is, if S is in mega and the voltage is in kilo, you still need 1,000, okay? And that's the 1,000 that you had in the lecture note. As usual, the safest way is go for volt, ampere, the base units. And always put these kind of numbers. But by practice and when you get more experience, then you know where to remove them or where to include. So, again, per unit reactance multiplied by the base reactance, this time you get 23.51. It depends on how you're approximating these values. That somebody may get 23.7, 23.8, 23.4. All of them are correct as long as they are within a range of, I mean, the difference is not more than 2-3%, that is fine. Now, section 3 is about changing the base. Okay, so the main base, or the original one, was 450, which was the rated power of the transformer. But this time they say change it to 200 megavolt ampere. In this exam, we didn't change the voltages. Maybe in your exam, we are also asked to change the voltages. So when you go to that big formula to transit from an old per unit impedance to a new one, you need to also include voltages. But here, voltages are the same, so you don't have to put this part in the formula. You can just write the shortest version. V per unit nu equals Z per unit old, S base nu divided by S base old.
So you always want to see it written before, if that makes sense?
Which one is it?
So you're saying
if they're equal, you don't have to write.
Yeah. Okay.
I'm writing here just to show that, okay, this is the main formulation, and in case they are different, you need to consider them. But if you see that we're not asking about a change in the voltage, you don't have to even write it. If you write, it's fine, but if you don't want, you can explain, yes, because you don't need it. So you can simply go for Z per unit new, Z per unit old, S base new over S base old. So new one is 200, and old one or given one is 450. The old or given per unit is 0.2. So you get 0.09 per unit as a new per unit value for this generator, for this transformer. Then the last part is now calculate the actual new value in ohm of transformer reactance on 200 MVA. So we changed the base. Now that we've changed the base, obviously we need to calculate the new base impedance. You cannot use the base impedance you had in section 2. You need to recalculate it, okay? So the procedure here is the same as section 2, but with new power. So new power is 200. Okay? 200. So voltage remains unchanged. Nobody asks us to change the voltage, so you take the same voltage in high tension side. They say difference to 230. So 230 kilo square over 200 million. And that gives you a new base for the high tension side. The new base is 264.5 ohm. Now, they say, what is the actual new value in ohm? Actual means ohmic, okay? So we go for ohmic. Ohmic equals per unit multiplied by base. But you need to be very careful here. If you just be careful for this part, you get a full mark here, because everything else should be very, I should say now it's trivial, and it's very, very easy. You should be careful here to use the new per unit. That's a common mistake I see. Some students use the old per unit here. So you need to use the new one, 0.09, and the new base impedance. And the new base impedance. So 0.09 and this new base you got here. So finally you get the same value, more or less, as you got in section 2. Because I said, when you change the base for the calculation, the ohmic impedance of the transformer doesn't change. It has nothing to do with the way you are doing the calculation. It is dependent on the type of material they're using, the conductors and the other things. It's actually something at the characteristics of the transformer. So 23.8 or 23.51. It depends where we are doing this approximation and where we had the error, but it should be the same actually. So you can, if you don't have any question, we can go to the second question. So, again, part of a distribution system. Although this is not actually the only case that you would see in the exam, but 99% of the cases, you see a portion of distribution network. In the lecture note, we had other examples, but most of them were from transmission system. As you're in the building services, you're going to do building services engineering, we take a portion of a distribution network. So this is a portion of distribution network. As usual, we need to define the fourth level of the coupling point with the upstream network. And you know that is modeled as a series reactance in the system. So when you go to map it, this fourth level is mapped as an excess always, okay? So the first thing, you draw the neutral line or reference line, ground, whatever, on top. You can draw it anywhere you like, but maybe it's easier to draw it on top. And then the first reactance is that excess, representing this fourth level. We see how to calculate it. The next one is this bus, B1, so this is B1. Then after B1, you start with the elements you see in the system. Transformer, for example, the series reactance. Then we see this B2. So this B2 is here. There are 3 generators. It doesn't matter if they're upside down or the other way. This figure, this single line diagram, just shows that there are 3 generators connected to this bus. And so we need to model them like this with reactances. From one side, each generator is connected to the same bus. From the other side, they're all connected to the neutral node. So they're all connected to the neutral node. After this bus, which is B2, there are 2 transmission lines. So these 2 transmission lines. And then the transformer. And the fourth point, B4, is where we want to calculate the fault. So this is the reactance diagram. To be more precise, this is actually impedance diagram, because based on data we had, we also model resistances here. That's why in the question they say equivalent circuit system expressing all impedances. So we are expressing also impedances. We are including the resistances. Later, for the fault calculations, we remove the resistances because we just need reactance.
Do you have to show the resistance?
Yeah, well, if it says impedance, expressing all impedances, yes, you need to include. Yeah. But then when you go to reducing, To be more precise, you need to include them up to the end. But as you need the reduction for short circuit calculation, from the beginning you can remove them. So you just show them here, you actually calculate these values and map them here, but right after this step, when you're going to reduce this network, you can remove them. That's fine. But here in this example, you see I'm not removing. I kept them, and you will see how I'm reducing. So we go to reduce, but before going to reduce, let's see how we got those numbers. So the first one is this part level 250, and I want to know what is that excess. Excess, we proved, I don't want to get back to the proof anymore, equals the new base power, in this example that is 2 MVA, divided by fault level. Okay? So new common base power, whichever is given in the problem, divided by fault level. So 2 divided by 250. 2 divided by 250. It's 0.008. 2 divided by 250.
So can you do it that way, or do you need to do it the way where you do 250 divided by 2 and then 1 divided by that answer?
Now if you divide 2 by 250, that's it. But
No,
the other way.
do you have to, can you show it that short way, or do you need to show it the longer way?
No, you can show it short way. Yeah, short way, yeah. No, you don't have to do that. But I was doing that because I wanted to show you from where we got that. That's not a, that was an extraction of a formula. And here, looking if I have it somewhere to show to you. I don't. Yeah, here. S base 2 MVA. So it's again like I'm going through the proof. So SF in per unit is 250, which is the fault level, divided by the base. So we get 125 per unit of fault. And we know X per unit is the inverse of this one because voltage is 1 per unit. So 1 divided by this I, because S could be also I per unit, equals 0.008. But you can just divide 2 by 250. And that is okay, that is correct. You get the mark there. So this is for the excess, and then we have the transformer with 10 MVA and 0.2. So obviously 10 MVA is different from 2 MVA. We need to have a transformation of the old one to the new one. So for that transformer, okay, we need to see where I have that calculation, but anyway, you need to just make 2 divided by 10 multiplied by 0.2. The new base divided by the old base multiplied by given per unit. So 2 divided by 10 multiplied by 0. Yeah, it's here. Yeah, 0.2, so this is for the transformer. But this is actually transformer 1, T1. X new for transformer 1 is X old transformer 1 new divided by old. So 2 MVA divided by 10 times 0.2. Next one, these generators. They have equal reactances, equal capacity, so we can just calculate for one of them. So generator new per unit equals given one 0.25, so 0.25 times new base, which is 2, and the old or given one is 1.5 MVA. 1.5 MVA. This is 1.5 MVA, and you get 0.33 per unit for all of these generators, each of them actually. Then there are 2 transmission lines. Again, transmission lines are usually with O. I mean, the impedances are ohmic impedances. So we need to firstly calculate the base impedance. then divide these ohmic impedances by the base. So base impedance here, Z base equal the voltage square divided by S. V square over S. Similar to question 1. Always base impedance equals voltage square divided by S. We need to see which voltage to put in this formula. 11, because this transmission lines are in the 11 kilovolts section. So 11 square divided by new base, obviously 2 MVA.
But does that not matter? One's in kilowatt and one's in mega.
That's what I discussed earlier. So I said, since this is kilo, so kilo square is like mega, because kilo is 1,000. When you make the square of 1,000, it's 1 million. So even if you include them here, if you write them, they would be equals 1,000. So you can just write kilovolts square divided by mega. You don't have to write them down. But again, it's safer to put them there and just cross them and get it, because okay, you do this here, it's okay, it's correct, but I don't want you to make a mistake when you go to calculate base current, because for base current, we don't have kilowatt square, we have kilowatt, and then power. So kilo is 1,000 times more, but mega is 1 million, so you should be careful. But here, for the base impedance, here you can just put kilowatt square divided by mega, because 10 to power 3 power 2 is like 10 to power 6, divided by here 10 to power 6, it will be removed. So you don't have to write. So this is your base impedance, and base impedance can be used for both resistance and reactance. So for both of them, we just need to divide the ohmic ones by the base. 1 divided by 60.5 and 2 divided by 60.5, and you get these values. Because based on definition, per unit quantity equals ohmic quantity divided by base quantity. The last one is this transformer. But if you look at this transformer, you see the rated power of this transformer equals the base power. 2 MVA, and this is 2 MVA. The rated power of this transformer equals the base power. So you don't have to do anything, you just take this value, 0.85. For the voltages, we've been fine. No changes in the voltages. We were only looking at the power, and when we see power is the same, so we can use the same per unit impedance. So that's why we had 0.85 here. You map all these values there, and the next step is to reduce this network. So I want to zoom in. Okay. So from here, to reach that single impedance, it doesn't matter how you're evolving the process. Somebody may do it everything on this diagram. Somebody may do it even by heart, just by doing some calculations. Somebody may want to redraw this several times, several iterations. So all of them are fine. Here is where it gets the mark for the reactance diagram, including correct numbers. Then the next step is you need to just get the reduction of this one. So that's a single impedance. So, for example, if I go to calculate these parallel and series impedances, firstly I pick these 3 impedances. When there are n parallel impedances with equal values, the equivalent one equals 1 divided, the equivalent one equals one of them, the impedance of one of them, divided by the number. Okay? So if you have, I don't know, 10 impedance, and each one is just 100, let's say, so 100, 100, 100, 100, 10. The equivalent one is 100 divided by 10. You take the impedance of one of them and divide by the number. Well, actually, the general way to calculate parallel impedance is you say the inverse of the equivalent one equals the inverse of the first one plus the inverse of the second one plus the inverse of the nth one. Okay? But the good thing here is they are equal, so we can just take one of them, divide by 3. So you can replace these 3 impedances with a single impedance with 0.11. 0.11. And this side we have 0.048. Okay? 0.048. And here, if you remove these resistances, again, these two are parallel with equal values, and you can just divide by 2. Now we see this reduction. Yeah, this one. Okay. So these 3 are replaced with 0.11. We just divided by 3. And 0.008 plus 0.04 will be 0.048. And for this part, again, we divided by 2.
So we can definitely get rid of the resistance.
Resistance, yes. So you don't have to go through the resistance because you don't need it. And yeah, and this is the last one. So now we've got that one on the right side. The two parallel reactances, you can calculate it, multiply them, and divide by the sum. And what you get here is connected in series with the rest of this system. So you add them. You add all those reactances, and finally you'd get this one. 0.9. You don't have to do the resistance. Well, again, this is for simplicity of your calculation, but in case you need to include resistance, you need to also calculate. But resistance is used for load flow and other applications.
So
here, our focus is on the faults.
why have you not added them together?
You can't add them because the different types.
But one's not. Which one's the resistance then?
This is resistance and this is reactance. If I put them correctly.
No, resistance isn't at the bottom. That 0.85 is a oh right.
This is a resistance.
Oh, okay, I understand. Yeah, so you just moved it to the bottom.
Yeah, I just changed something. Yeah, but you can't add them because this is actually 0.9J. It's not 0.9. For simplicity, you didn't put J, but this is 0.9J. Because this is in complex number, this is actually the imaginary part, and this is the real part. They together form impedance. The impedance V or R plus JX. This is a complex number, you can't add them algebraically. They're like two vectors, it's 90 degrees of phase difference. But okay, since we are forming this reactance diagram only for short circuit analysis, we don't need the resistance. In the next step, we only focus on the reactance. So next stage is calculate the per unit fault current for a 3-phase symmetrical fault here. The students in this exam were lucky. They had only one scenario to get 8 marks. But sometimes you see there are 2-3 different configurations. So just one calculation here you need, and that is...
Are we going to be lucky?
I don't know. I usually make 2 versions, that's how it was say. One is the easy one, the one is maybe a bit different. And then first you decide which one to take for the main exam.
I feel good.
Just give it
So, yeah, you see IF again, VF over the impedance, the 0.9, and you get 1.1 per unit. And 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 per unit fault, so that's it. That is the per unit fault, 1.1. Next step for section, calculate the actual fault current and fault level for the symmetrical fault here. So now we need to convert the per unit to ampere and to MVA. So actual fault current is in amp and actual fault level is in MVA. So for MVA, we are fine. We have the common base power. We just need to multiply by this value. So that is fine. You see, 2 MVA is given. This is the base power. You multiply it by this fault, and you get 2.22 megavolt ampere. This is called actual fault level.
Actual fault level.
Level, which means actual fault power. Then actual fault current is current. So you need base current in order to obtain it. So you need to calculate base current. Here in my notation, base current, the inverse of base current is calculated simultaneously with the calculation of the actual fault current. But you know, base current equals S base over root 3 V base. Okay? And as we multiply by the per unit value, we take this exact base current here. So S, so this is not the inverse, this is actually the base current. So this is S base times per unit fault. Okay, S base times per unit fault, together 2.2 times 10 to the power 6, divided by root 3 and the voltage.
When we done this question the other week in class, when we done the 3 scenarios, so it said identify the fault currents at V4 from the 3 scenarios, so like generate 1, generate 2.
Yeah.
We done the base first, and we didn't. So basically, we done SB over square root of 3 times VB.
Yeah.
And then that.
And then you multiply it by 30.
Yeah, we've done the base voltage times the IF.
Yes.
But that gives you a different answer to that.
No, it's the same. Here I actually merge them. I put them. You can now calculate. Okay, you can now calculate the base current here. You can calculate the base current for this one. Once you've got the base current, you need to multiply by this.
Yes. But when I did that yesterday, I got different answers. I got 2,500 and 4,000. Different ways, so it didn't make sense.
It should be the same unless you are making some numerical mistakes. Because what here you see is actually base current times 1.1. Nothing more. So base, what is base? 2 million. 2 million times 1.11. That's it.
So you just did it in 1 or 2 steps?
Yeah, because this is just for the marketing purpose. So when I go to explain to you, yeah, obviously I did it in 2 lines.
Yeah, I just tried it both ways. I couldn't answer.
But you should get the same answers because you see, what I'm doing here is just multiplying that base current by this 1.11. Nothing more.
Yeah, so you're doing an IB versus IF.
IB, this is IB, times 1.1. So it's like 2 times 1.1. That's 2.22 million, this is mega, divided by root 3. And voltage, be careful, here the voltage is volts, not kilovolt even. That's why I always say that maybe it's safest to go for the base units. Here we have 10 power 6, here we don't have 10 power 3. Because this bus is a low voltage bus. 415.